This lecture is entitled Bringing Truth to Light, and it's going to introduce you to some of the fundamental concepts that we have about light. And the quote we have says, "We can easily forgive a child who is afraid of the dark. The real tragedy of life is when men are afraid of the light." And so that's a famous quote by the philosopher Plato. So let's look at our learning objectives for this particular lecture. And our learning objectives for this lecture are: number one, that you understand that light exists as both a wave and a particle, that you understand the relationship between frequency, wavelength, and energy in the electromagnetic spectrum, and that you be able to use several of these formulas to calculate for an unknown variable. Now that looks like a lot, but all of these formulas have been introduced to you before. C equals d over t is just from earlier this year. We talked about velocity as displacement over time. C equals lambda f, we talked about in the last unit. We just called it V equals lambda f. So that's nothing new. And then finally you have E equals hf, which was introduced to you in chemistry. So what you already know. You should already know that waves are traveling energy. We've already talked about that. They have characteristics that are different from normal matter because they aren't matter, they're energy, such as being able to occupy the same space at the same time, things like that. So, what we learned in the lab is that white light actually consists of many different colors. Specifically, we said that there were primary colors that were red, blue, and green. And that's different than what you've experienced if you've had it in art class. They tell you that they're a little bit different. But those are the primary colors of light. We also learned that these colors have different amounts of energy, with red being the lowest and blue being the highest that we tested. And using the polarization lenses, we should have been able to figure that light actually consists of two electromagnetic waves. A polarization lens will block out one of them and allow the other one through, appearing to dim the light. So the question is what is light? Is there a definition for it that you can see? We use light a lot. We see with light. You use light for flames. You use light in paintings. We say paintings look different in better light. You say, oh, I like the way this light looks on this. But if you had to look at it, what would the color blue be for somebody who was blind? And it's very difficult to do. So let's look at what light actually consists of. One is the idea that light consists of photons, and photons are particles of light or packets of light that move through space. And the reason why we have this idea of photons is mechanical waves that we covered earlier, sound, a slinky, those sorts of things, they actually required a medium in which to travel through space, and we know that light can travel through empty space. So there's this idea that light consists of particles that are able to move through space just like matter can move through space. Now there's evidence of the there's evidence of the opposite as well, and that's the idea that light does have some wave-like properties. Light does things that wave does. It can reflect, it can reflect, it can refract, it can form interference patterns, and that's actually what you see right here. You have two sources of light, right here and right here. And what happens is those light waves get to the point where they interfere with each other and they produce an interference pattern. So there is some evidence that light itself is actually a wave. But there is also some evidence that light is a particle. And that's what you see here when you look at this famous experiment was called the photoelectric effect. And it was showing that light has to have a certain color in order for it to actually make electrons bounce off and light up a light bulb. And so this is a little bit beyond what we're talking about, but the idea that a wave could not accomplish this led people to think that photons existed as particles of light, and a photon had to have a certain amount of energy to knock off an electron. Another basic idea for this is the idea that a photon can have a definite position. We can say that this particle of light is here, and therefore you have to think of it as a particle. We can also model light is moving in a straight line, and light can collide with stuff. So because of that, there's evidence that it has to be a particle. So we have evidence that light is a particle. We have evidence that light is a wave, and we're going to explore that in just a minute. But a lot of people get hung up on the idea that you can't see a photon. Well, if you were to look at this, they're so incredibly small that you can't detect them. So if you were to take a look at this particular painting right here, the painting looks pretty uniform. It looks like there's green and then there's browns and so forth like that. But whenever you zoom in closer, you actually start to notice that there's imperfections in the canvas. And as you zoom in closer to what a photon of light would look like, you actually see these kind of gaps. So the analogy isn't perfect, but it's pretty good. The fact that photons are so incredibly small, you're not going to be able to see them. Instead, you can only detect the larger picture of many photons together acting as a color. Now, properties of photons. A photon is said to have zero mass. Now, this gets kind of tricky the further you go along in physics. It turns out that it has zero rest mass. So whenever you have a photon that's just sitting here on the table, it's said to have zero mass. When it's moving, it's said to have some mass, and that has to do with the fact that mass and energy are related, and we will get into that in the last 6 weeks. All photons are said to travel at c, which is the speed of light, which we will talk about, but is 3.0 times 10 to the 8th meters per second. Okay, so you have this value, and they all travel at this. And that the energy of each photon is related to the frequency of vibration for each photon as well. So the question is this: we have evidence that light's a wave, we have evidence that light's a particle, so what is light? And the answer is it's both. You think of wave as being black and particle as being white, and it's actually somewhere in between. It's shades of gray. It exhibits both wave and particle behavior, so we say it exhibits something we call wave-particle duality. So whenever somebody asks what light is, you have to say it's both a wave and a particle, not either or. So there's a little video that you can watch, and your teacher will have this queued up for you in your presentation, but it's a little video that actually explains the idea of wave-particle duality and some of the different experiments that were done in order for you to see this. So it's very important that you take a look at this in class. Another example of the idea that you have this wave-particle duality is Young's double-slit experiment. Now, Young's double-slit experiment was originally done to show that light was in fact a wave. And that was a great evidence that light was a wave. But it turns out that when they repeated the experiment not with light, but they also did it with electrons, you had the same exact effect. You got this interference pattern. And so what that was able to show us is, according to this experiment, that light is a wave, yes. But it also showed us that you can have matter like electrons and you shoot it through, and it also exhibits wave-like behavior. So this is another experiment that kind of proved the idea of a wave-particle duality. And basically what you're seeing here is, as the electrons or the photons go through, there is a definite pattern as far as what you see. You see the idea of when you have a single slit, there is no interference between anything. You have a single peak. But whenever you have a double slit, that allows for interference. Instead, you see these multiple peaks. It goes up and down, and that represents the bright and the dark spots that we saw in the previous image. So you have bright and then dark, and you have alternating patterns, whereas if you had the single slit, okay, the single slit would just produce a solid color. Now, light you can think of as a glimpse to the past. Light takes time to travel. Even though it seems instantaneous to our senses, light still definitely takes some time in order to travel. So you can think of everything you see as what it looked like a certain amount of time ago. Whenever you're looking across somebody at the room, you're actually looking at what they look like a fraction of a microsecond ago. So we can oftentimes say that we're looking into the past by looking usually out into space. So if you were to take a look at it, this is a picture of the Hubble Ultra Deep Field. And what it does is that actually shows you a picture of a wide range of the sky. And if you were to look at this, how many stars do you think you see? And the answer might surprise you in the fact that it's 2. And you see all these lights and you're like, well, there's a ton of lights everywhere. How come, where are all the stars at? Each one of these little dots right here represents a galaxy of stars. So these are all galaxies representing billions, millions and billions of stars. So in this one picture, you have an incredible amount of stars that are going on there. Most of these stars are extremely far away. Some are as far as 13 billion light years away. Because they're 13 billion light years away, they're so far away that when we look at the light that comes to Earth, we don't see the stars the way they are now. We see the stars they were 13 billion years ago. So looking at the stars is a way of looking at ancient history. Whenever we say, what was the universe like 13 billion years ago? It's not like we're inventing a time machine and going back. No, we're looking deeper into space. And when we look deeper into space, you see stars that were further away. And so you see what they were like that time ago. Now, the speed of light is one of the great constants that we have in physics. In fact, it's represented by the value c. The reason why we call it c is because it is a constant. This is the same formula that you learned earlier this year as velocity equals displacement divided by time. It's the same thing. The only difference now is instead of referring to it as velocity, we refer to it as the value c because the speed of light in a vacuum is considered to be a constant. And that constant is 3 times 10 to the 8th meters per second. So let's work out some examples. It says the first one that we have here says, as your teacher gestures at the front of the room, it seems like it's happening all at once. It seems like there's no delay. How much time passes between the teacher moving and the light reaching your eye if the teacher is 3 meters away? So this is just an example of us using the formula C equals D over T. You were given this right here, and that D is the distance, which is 3 meters. You are also given the speed of light, which is a constant, and that's something that you need to know. It's 3.0 times 10 to the 8th meters per second. Okay, now you take these values and you can plug them into the equation. So you get 3 times 10 to the 8th equals 3 divided by t. You rearrange the equation, multiply both sides by t. Now you can divide both sides by 3 times 10 to the 8th. And when you do that, you get an extremely small value for the time. In fact, the time ends up being something like 1 times 10 to the minus 8th seconds. Just to put that in perspective, the human body is only capable of detecting things that are about 1/60th of a second. So we can't detect things that are 0.01, let alone 0.00000001. So this is an extremely small value, and that's why it appears to be instantaneous to us. In the next example, it says the Andromeda Galaxy is our nearest cosmic neighbor. It takes light 2.5 million light years to travel to us from there. How many meters are there between us? So if you were to look at us, we're over here. The time that it takes to go is 2.5 million years. So we're going to say that's 2.5 times 10 to the 6th years. And you should realize that we can't really deal with that value. Instead, what we're going to have to do is convert years to something we can deal with, which is seconds. In 1 year, there are 31,557,000 seconds. And if you don't know that from the movie Rent, then you can always multiply it out, and you can say there are 60 seconds in a minute times 60 minutes in an hour times 24 hours in a day times 365.25 days in a year. And you end up with the value of 31,557,000. So now once you have your value in seconds, which is 7.89 times 10 to the 13th, now we just plug it in just like we've been doing. We say C equals D over T, or in our case it's 3 times 10 to the 8th equals, in this case I'm trying to solve for D, divided by 7.89 times 10 to the 13th. I multiply both sides by 7.89 times 10 to the 13th, and when I do that, I get a value of D equals 2.37 times 10 to the 22nd meters. Next, we talk about the electromagnetic spectrum, and most people refer to it, they say, the electromagnetic what? And the idea is that light, or what you see, is a very, very, very small range of the possible frequencies of the electromagnetic spectrum, or photons of quote-unquote light. So we call this thing the electromagnetic spectrum, and it helps if you can kind of visualize it. So let's take a look at it. You see this. So we start off with the idea of radio waves, and radio waves right here are the longest ones in terms of size. Radio waves can be, up to a kilometer in length, as far as one complete wave would take a kilometer in length, all the way down to where you have the gamma rays, where gamma rays are operating on the order of 10 times 10 to the minus 12th meters. So they're extremely small. They're the size of individual atoms. So you have this giant range of the electromagnetic spectrum, and the part that we can actually see is right here, and it actually tends to be the smallest part of the electromagnetic spectrum. It doesn't look like it, but if you look like this right here, the scales are very different. If you look for the whole range of visible, it's going from here to here. That barely goes from about 10 to the 14th to 10 to the 16th, whereas you have much, much wider ranges for things like radio. Okay, you're talking about 10 to the 4th to 10 to the 8th. Now, you need to know the general order of the electromagnetic spectrum. You need to know that it goes radio, microwave, infrared, visible, UV, X, and gamma. Now, the most common way that people remember that is the idea that you have red Martians invade Venus using X-ray. X-ray is nice because it fits, and then guns. If you start off with this idea that red Martians invade Venus using X-ray guns, that tells you the order of the spectrum. Now, what it's telling us is it's telling us the order from wavelength is large to wavelength is small. Or, if we looked at it on the frequency scale, it's saying from frequency is small to frequency is large. So it's up to you, once you know the order, to say, okay, I'm going from low frequency to high frequency when I do this, or I'm going from high wavelength to low wavelength. And it's really important that you be able to do that. In addition, you need to know how they relate in terms of energy. As we'll explore a little bit later in this presentation, frequency is directly related to energy. So if I have a low frequency, I have a low energy. If I have a high frequency, I have a high energy. So, but what can you see? Now, if you look at it, this puts it a little bit more in perspective. What you can actually see is this very tiny part called the visible spectrum, and it's broken into colors where you have violet, blue, green, yellow, orange, red. Now, if you notice, this electromagnetic spectrum is actually turned around backwards, where you have increasing wavelength and decreasing frequency. Sometimes that happens, so you've got to pay attention to what you're looking at in terms of wavelength and frequency. So if you look, here you've got radio, then micro, then visible, and it goes up from there. But the parts of the spectrum that you can see are these colors right here, oftentimes abbreviated as Roy G. Biv. Okay, and a lot of times they leave indigo out, sometimes they put indigo in, but you got this idea of Roy G. Biv. Now, if you think about it in terms of energy and things like that, you have increasing frequency this way, which means that violet has much more energy than you have for red. That's one of the explanations why most laser pointers tend to be red, is because if you had a violet laser pointer, it would be much more energetic and potentially much more harmful. So let's explore these relationships in a couple of examples. The first one we have here says, form an explanation as to why it is dangerous to be in a room with X-rays, but not to be in a room where radio waves are used. So if we look at radio waves have a very large wavelength, they have a very low frequency, and they have a very low energy. Whereas X-rays have a very low wavelength, they have a very high energy, and they have a very high frequency. And if you look at it in terms of damage to health, there's a couple of things that you can look at. The first one is the idea of wavelength. The smaller a wavelength is, the more likely it is to be able to penetrate the skin. It can penetrate the skin. So the first reason why we have X-rays as being dangerous is they can actually penetrate the skin, whereas radio waves cannot. So that offers us a first kind of glimpse of what could be potentially damaging. The second part is the idea that radio waves are very low in energy, whereas X-rays are very high in energy. So when you put those two factors together, you should realize that, okay, if it can penetrate the skin with a lot of energy, it's got a lot of potential to do damage. Next, it says what color laser would have the highest probability of marking a target without detection. And if you're going to use the visible spectrum, the best bet would be red. And the reason why is because it has the lowest energy. Okay, we tend to detect things that have high energy. So you're not going to notice a red dot. You're not going to feel it as heat. It's not going to glow quite as much as when you have, blue or orange or something else. So whenever you're marking a target, a lot of times they will use red as opposed to any other color. Now, most often they tend to use something called an infrared laser. And the reason why they use infrared laser is it's very close to red, but it's actually below what can be seen. And if you can't see it, there's much, much less likelihood of detection. In this example B3, it says rank the following in order of increasing frequency, and then you have the idea of ultraviolet X-ray, and it lists all the parts of the EM spectrum. So remember, if you remember red Martians invade Venus using X-ray guns, the only thing you have to decide is, does it go this way or does it go this way? And if you remember, radio has very, very low energy, and those very low energy have very low frequency. That's related. So if I want to do it in terms of increasing frequency, it's exactly how I wrote it here. You would go this way. Red Martians invade Venus using X-ray guns. Okay, you need to commit that to memory. The speed of light allows us to relate the variables of wavelength and frequency. Now, you've actually seen this formula before. We just called it v equals lambda f in the last unit. The only difference between that formula and this formula is the fact that we have v, that's an established value of 3 times 10 to the 8th, just like we had in c equals d over t. So there's nothing new here, just like there is before. It's just the fact that you have to incorporate the value of c. If you look at this example, it says one type of military radar referred to as the CXAM operates at 2 times 10 to the 8th hertz. Describe if this radar should continue to be used with the advent of miniaturized drone technology. And then it says justify your answer using the clear method. So once again, we're going to take this idea of c equals lambda f. Now c is a given value. It's 3 times 10 to the 8th. Remember, that's the speed at which all electromagnetic waves operate. You also have this 2 times 10 to the 8th hertz right there, which actually is the frequency. So whenever you take those two values and you plug them in, you can actually solve for the wavelength being about 1.5 meters. Now that allows us to address the question. The question says, should we use this radar in the advent of miniaturized drone technology? You actually just see a picture right here where the drone is about the size of somebody's fingers. So since that is much, much less than 1.5 meters, the drone is smaller than the wavelength. This particular radar wouldn't be able to visualize or wouldn't be able to see a drone because the wavelength is larger than the object itself. In order for you to be able to see an object, the wavelength has to be smaller than that particular object. This example says if you listen to a radio station at 102.9 megahertz, that's 1.029 times 10 to the 8th hertz, that has a wavelength of this, what is the velocity of this particular radio station? Now, we should know that the velocity should be about 3 times 10 to the 8th meters per second. And the reason why we know that is it's a radio wave. And a radio wave is the same as a light wave. So, if we plug in our values like we do into the formula c equals lambda f, we can actually get the value. 2.916 is the wavelength. That's our wavelength. And then the frequency that we have is going to be 1.029 times 10 to the 8th hertz. When you multiply all of those values out, you end up getting a value of about 3.00 times 10 to the 8th meters per second, which is exactly what I would expect. A lot of people see the idea of a radio wave and they think it travels different than the speed of light. But remember, all parts of the electromagnetic spectrum will travel with the same velocity. And this next example says a red laser has a wavelength of 681 nanometers. Now, a lot of times you will see the wavelength of light reported in nanometers because it's a more common unit. You're not going to say 6.81 times 10 to the whatever. So it's a lot of times you'll see it in nanometers, but it's up to you to be able to convert those values. Because we're talking about light, we know that we have the value of c is 3 times 10 to the 8th. We also have this value right here, which needs to be converted into standard units. When you do this, you get 681 nanometers, and there are 1 times 10 to the 9th, or a billion, nanometers in 1 meter. That means that this value for the wavelength is now 6.81 times 10 to the minus 7th meters. Once you've established the value of the wavelength and then you have the speed of light, you can plug it into the equation c equals lambda f. Or in our case, 3 times 10 to the 8th equals 6.81 times 10 to the negative 7th f. Divide both sides by 6.81 times 10 to the minus 7th. And when you do that, you end up with a value of the frequency being rather large at about 4.4 times 10 to the 14th. In this next example, it says if the Chandra Observatory satellite observes some light that has, light, remember we're talking about the EM spectrum, that has a wavelength of 0.57 nanometers, and this is what kind of electromagnetic radiation does the Chandra Observatory view. So in order to do this, I'm going to go ahead and use the formula c equals lambda f. When I do the formula c equals lambda f, remember you still have 3 times 10 to the 8th. The problem is I have 0.57 nanometers again. So I would say 0.57 nanometers, and I would say that there are 1,000,000,000 nanometers in 1 meter. That would give me a value of about 5.7 times 10 to the minus 10th meters would be our distance right here, or our wavelength. You can now take this value and you can plug it in here for the wavelength, and you can solve for the frequency, just like we did in the previous example. Now whenever you do this and you divide everything out, you get a frequency. Let's go ahead and make a little room. You make a little frequency of 5.26 times 10 to the 17th. Now the last step that you actually have to do is you have to use this information to try and identify what part of the EM spectrum it's looking for. So you could look at an EM spectrum, and when you do, it'll tell you the frequency, and you should realize that this is looking at X-rays. In fact, it's called the Chandra X-ray Observatory is what it's called. The last part of this particular lecture is the introduction of the formula E equals HF. Now I say introduction, this formula is actually covered in chemistry, but we need to revisit it when we talk about physics. So you have this idea that E equals HF. Now F you already know is the frequency. E you should know by now represents the energy. But in this particular case, it's talking about the energy per single photon. This formula is the idea that you can calculate the energy of one photon given only the frequency. Now you do have this H term in here as well. And H is a constant. It's called Planck's constant. It's really important in terms of quantum mechanics we talk about a little bit later. But it's the idea that this is the lowest amount of energy that a particular photon, or actually anything, can have. It's called Planck's constant. And it's a value of 6.626 times 10 to the minus 34th. That's the only thing that's really new. Now, a lot of times you will see this formula slightly different, and it's really important that you be able to see, say, when to use which. A lot of times you will see it as E equals NHF. Now, this N term comes from this is the number of photons. So if you were trying to determine the amount of energy in 1,000,000,000 photons, you find the energy of one photon, and then you multiply it by the number of photons that you actually have. So the N is usually 1, and that's why it cancels down to this whenever you're looking at a single photon. So let's look at an example. It says if a beam of light with a total power of 60 watts emits photons that each have an energy of 3.98 times 10 to the negative 19th, how many photons are emitted by the beam of light? Okay, so you have 60 joules is what is produced. That's my energy value. Now you also have the amount of energy per photon, and a lot of people will try and immediately plug this into the formula. But when I write it out like this, hopefully you can see, using dimensional analysis, how to solve this. You have joules and you have joules per photon, and what I want to know is I want to know the number of photons. So if you were to look at this, I could take 60 joules and I can divide it by 3.98 times 10 to the negative 19th joules per photon. Looking only at the units for now, the joules is going to cancel out with the joules, and since photons is on the bottom of the denominator, it will flip up to the top, leaving you with just units of photons. So if you take 60 and you divide it by 3.98 times 10 to the negative 19th, that'll actually allow you to calculate the number of photons that are present, and that is about 1.51 times 10 to the 20th. So that's a lot of photons. Now if you think of something, there's something very similar to this 60 watts, and when you have something like a 60-watt light bulb, you're looking at an incredible amount of photons that are produced every second. So in the next example, it says if a photon has a wavelength of 2.6 times 10 to the minus 13th, how much energy does it transmit? So we're looking for the energy here, and in this case you're given the wavelength. Now the formula that I have for energy does not have wavelength in it. It's E equals HF. And you look at that and you go, okay, well I have no way to solve this except for the fact that you have another formula as well, which is C equals lambda F. A lot of times these two formulas are combined to make the equation E equals HC over lambda. If you do this, it shows the inverse nature of the fact that as wavelength goes up, energy goes down. Now H and C are both constants. And a lot of times those are put together when you start to look at things like quantum mechanics. So when we take this, we can plug it in. We can say 6.626 times 10 to the negative 34th times 3 times 10 to the 8th. And we divide it by our wavelength value, which was 2.6 times 10 to the negative 13th. And we would put that in our calculator. And when you're doing it in your calculator, you actually have to be really, really careful to put in the exponents correctly. The most mistakes that people make are with the exponents at this particular question. So when you do this, you actually get an energy value that's it's not very large, which makes sense because you're talking about the energy of a single photon. It ends up being about 7.6 times 10 to the negative 13th joules. In this next example, it says a red laser operates at 4 times 10 to the 14th hertz. How much energy does each photon have? So we're going to use the idea of E equaling HF. And in this case, I'm given the frequency straight away, and H is a constant, so you can just plug in 6.626 times 10 to the negative 34th times 4 times 10 to the 14th. When you multiply those two values together, once again being very careful about your exponents, you end up getting a value of about 2.65 times 10 to the negative 19th joules. Now remember, once again, that's a low value because we're talking about the energy for every single photon.